Okay, hi everybody. Let's start. Okay, we have more people today. That's good. Please feel free to turn on your videos. And yeah, so today we have a new subject, which is generating functions. And so it's going to be a little bit more abstract, especially in the beginning, but I think that's worth it. So it's going to be, we're still interested in counting things, but using a new tool. So, okay, I see 0 faces. All right. Yeah, and so as usual, I'm going to pretty much follow our usual textbook, but every once in a while, I'm going to tell you something from the book of Richard Stanley, Enumerative Combinatorics Volume 1. It's available online for free from his webpage. And yeah, it's, to my liking, it's slightly more rigorous. I'm going to try to be as rigorous as I can. Okay, so, and also, by the way, thanks to all of you who submitted the feedback form. If you haven't, and if you have any complaints, please don't forget to let me know. I might actually fix some problems. Yeah, so let me try to set things up with the generating functions. And the idea is very simple. So we're going to consider what is called a formal power series. Formal power series it's just a formal sum. It's a sum of the form just take any arbitrary sequence of, let's say, complex numbers. So where f0, f1, it just goes up to infinity. Any sequence of, yeah, let's say complex. Mostly we're going to consider integers, but complex numbers. So, and that's already an important distinction. In calculus, you learn that, okay, the series has to be convergent, otherwise it's not well defined or whatever. But for us, we're not gonna care about, so we do not care about convergence at all. So in other words, formal power series are just another way of writing down a sequence on any sequence of complex numbers. It's just another way of recording the same information, right? And yeah. And so, but why that so far it's pretty stupid. But the trick is that we're gonna, if you write it down in this form, then you can manipulate these generated functions in these formal power series in such a way that in a way that's not really clear from the combinatorial perspective, but very useful from it gives you powerful results in a non-obvious way. So the first two things you can do with power series is you can add and multiply. So you can add power series and multiply. So how do I add two power series? Let's say I have one sum, a sub n x to the n, and I have another power series, bn x to the n. So I add them up. That's very. I always kind of follow the usual rules of algebra. So there should be no surprises here. And for multiplication, it's a little trickier. So if I want to multiply, two power series, then I get another power series, which is so it's defined by, again, usual algebra rules, right? If you, let's say, if these two are just polynomials, then what would Cn be? Cn is just the sum for I from 0 to n, ai, b, n minus I. Right? That's how I would multiply two polynomials. And now the degrees are bounded from below, but they can go up to infinity. So still, this sum is well defined. So the product of two formal power series gives me another formal power series. And for those of you who know algebra a little bit, this is such an algebraic structure is called a ring. So formal power series form a ring. So if you know what it is, then great. And if you don't, it doesn't really matter. And yeah, what matters is the notation, which I'm going to denote C double bracket X. So if C usual bracket X is the polynomial ring, and it is sort of contained inside this double bracket formal power series ring. So, and if you don't know, a ring is a structure where you can add and multiply. So maybe like matrices or integers, you cannot always divide, and we're going to discuss that. But you can always add and subtract and multiply and do whatever. Yeah, so, and that's the ring that's the structure we're gonna work with. So yeah, any questions so far? All right, no questions. Yeah, okay. So now let me talk about division. As I said, I cannot always divide, but I can divide sometimes. So as usual, let me say, here's a definition. If you have two power series, f of x and g of x, which happen to, so their multiplication is well defined. If they happen to, if their product is equal to 1, then we say that g of x is f of x inverse, or like 1 over f of x. Right? So if you give me f of x, then its inverse may or may not exist. But if it exists, it is unique. Which is, yeah, I guess I have to prove it, but I mean, it's an exercise. It's just a general fact that this ring is a unique factorization domain. So if you have a product of two things, anyways. It's very easy to see just from the definition of multiplication. If you know the a's and you know the result, then you can recover the b's uniquely. Basically, that's the, if you can, then it's unique just because of the system of equations you get. And let me try to give you a couple of examples. So examples. So first of all, as I mentioned, any polynomial p of x, just if you take a finite sum, then it's a special case of an infinite sum, is a formal power series. And in particular, right, you have just one. One is just by definition 1 plus 0x plus 0x squared plus etc. So it's a valid formal power series, which is the unit of my ring. So if you multiply anything by 1, you get the same thing. And now, so here is I claim that if you give me a power series, right, so I can take any polynomial. So let's say I take 1 minus x, then this guy has an inverse in the ring of formal power series. That is given by g of x, which is 1 plus x squared plus etc. Just all coefficients are equal to 1. So, which, yeah, I can write it like this, right? 1 over 1 minus x, where by definition 1 over 1 minus x is the inverse of 1 minus x. So, and I have to prove it. I cannot just, I mean, you all know things about geometric progressions and stuff like that, but still, like formal power series is a new object. You can't, I mean, you can't right away just translate all results from calculus to formal power series. But the whole point is that all computations are inspired by calculus, and that's where the power comes from. So let me try to prove it. I need to prove that f of x times g of x is equal to 1 in S power series. So how do I do this? Well, I just use the definition. So I just did the definition, which is that if I if I just compute the product, right? So 1 minus x times 1 plus x squared plus etc. If this is equal to the sum over n greater than or 0 cn x to the n, just by definition of the product on the two formal power series, Cn is, I mean, it's equal to, the sum is basically 1 minus x plus x minus x squared plus x squared minus x cubed plus etc. So, and these Cn coefficients are obtained by summing these two. So Cn is either 1 if n is 0 or 0 otherwise. And that's why the right-hand side is equal to 1. So yeah, what I'm doing, it sounds very trivial, but it's an important distinction. You can't, you have to be very careful when you just say something is true for functions and therefore it's true for power series. You have to kind of be able to verify it formally using the product and addition formulas. So let me also mention that the more general formula, which is very useful. So if you more generally, the same proof shows that if you want to invert 1 minus alpha x, and then the result is just going to be the sum of alpha x to the n for n greater or equal to 0 for all complex numbers alpha. So yeah, so these are examples of elements which, like 1 minus alpha x, has an inverse in the formal power series. Let me give you, or maybe somebody can give me an example of a function which does not have an inverse as a formal power series. X. Nice. Yeah, thank you. That is the intended answer. So if you give me an x, then this does not have an inverse inside the. As a formal power series, you can't really. If you try to solve the same system of equations here, you run into a problem because 1 over x, probably anything without a constant term. Yeah, probably. That's going to be a homework problem. So homework problem would be to determine which formal power series have an inverse. Just factor the x out and get a contradiction. Okay, you're giving me the proof that x does not have an inverse. Yeah, I guess that's the. Also, if it has a constant term, can't you construct an inverse? I mean, yeah, you're going to figure this out in the homework. Well, yes. Okay. Anyways. So there are more complicated examples of formal power series which come from calculus. So one example which is going to be extremely useful to us is the exponential of x, which just by definition is the sum of your coefficients, so just 1 over n factorial. So that's a formal power series. Yeah, this one happens to converge for all x, but some others converge. Yeah, so maybe you can also write down the sine of x, or the log of x, just like any hyperbolic functions. You can take the Taylor expansion of any that's called analytic, I guess, an analytic function. So any function that has a Taylor expansion, of course, gives you an example of a formal power series, which also happens to converge. Can somebody give me an example of a formal power series which does not converge for any non-zero x? 1 plus x squared over 2 plus x cubed over 3. Okay, that one's actually. Oh, okay, that is interesting. Now let me try more examples. So, okay, 1 plus x squared over 2 plus x cubed over 3 plus etc. I think that converges. So this converges. Okay, so yeah, I want an example for all. So for any, I want an example that does not converge for any non-zero x. This one converges for maybe x less than 1, right? Well, the absolute value of x less than 1. And the other one, 1 plus x plus 2x squared plus 3x cubed. Okay, let me try that one. 1 plus x plus 2x squared plus 3x cubed. I think this one also converges, right? You have a polynomial function times if x. Yeah, I think the same. Yeah, that should converge for absolute value of x less than 1. Any other examples? 1, 2, 4, 8, 16. Okay, interesting. 1 plus 2x is 4ax squared plus 8x cubed plus etc. I think this one converges when the absolute value of x is less than 1/2. If I understand your example correctly. You see, you need some function which grows faster than exponential. I wonder if we know some function that... Oh, okay, so factorial then. All right, yeah, that is correct. So if you take the sum of n factorial times x to the n, this one never converges. And yet, it is still a formal power series. All right, so the bottom line is that we don't care. We don't really care about convergence at all. This is all of our results. If we say that something is true for all formal power series, it has to be true for this guy as well, which you can't really say, like, you can't really apply any intuition, well, any formal results from calculus to this series. What about negative to the n, x to the n? Negative 1 to the n, x to the n. I think this is... Yeah, I think this converges for absolute value less than 1. Yeah. Okay, so yeah, so these are all convergent examples. Should I? Yeah, let me try to do this. Okay. Oh, all right, never mind. So now these are sort of general statements about formal power series. Now let me try to talk about sequences of interest to us. So yeah, let's say I have a sequence of interesting numbers which I want to count somehow. Maybe, you know, the Bell numbers or whatever. So let's say f0, f1, f2, etc. So I can do two things with it. So the first, and each of them is useful, and you gain it by experience to figure out which one to take. So the first thing I can do is to take the ordinary generating function, which I'm going to abbreviate as OGF. And this is just by definition the same thing we did above, fn x to the n. Another thing I can do is I can take the exponential generating function, which I'm going to abbreviate as EGF. So, and here I do something slightly tricky. So I take fn times x to the n, but then I divide each coefficient by n factorial. So these are two ways to record just a given sequence of numbers. And I already told you how to add and multiply generating functions like this. So these are both of these are formal power series. So you already know how to add and multiply. Now let me try to copy the rules for addition and multiplication. Oh yeah, maybe. So question is what is the rule to add and multiply exponential? How to add and multiply two exponential generating functions. So I'm going to divide each x to the n by n factorial. And the addition is going to just work the same. Right? So if I have two sequences a and bn, then the sum of generated functions corresponds to taken the sum of the exponential generating functions. But if I take the product of two exponential generating functions, then I get something interesting. So if I want to, right, I get some other formal power series where the coefficients, where d sub n is what? I have to expand this product. So I mean, I can just apply the rule for the usual. If I treat these as usual formal power series, then it's the sum. So if I take the coefficient of x to the n here, it's going to be the sum over the sum of I from 0 to n, the coefficient of xn here times the coefficient of xi here times the coefficient of x to the n minus I here. So xi, well, just ai over I factorial times bn minus I over n minus I factorial. That's just by definition, the product of two formal power series is given in this form. But then I can transform this, right? I can multiply through by n factorial, and I get d sub n is equal to the sum over I from 0 to n, ai times bn minus I times n factorial divided by this I factorial n minus I factorial. That's n choose I. Right. So there is some combinatorial significance to these exponential generated functions. Even though I'm doing a very simple thing, I'm dividing each coefficient by n factorial, the addition rule now involves binomial coefficients, just kind of naturally. And yeah, so let me try to use it. Let me try to maybe, where does the n minus I come from? Oh, you mean this n? If I just take the product of the two usual generating functions, then I get ai times b n minus I, right? Because that's how you multiply polynomials. When you multiply two polynomials, you have to take the coefficient of, to get x to the n, you have to take x to the I and x to the n minus I from the two. Okay, yeah, thanks. So yeah, so I'm just, so far I've only been using very elementary algebra, nothing fancy going on. Yeah, and now I'm going to try to invert. I'm going to try to invert something else, which is, maybe I can even ask you a question. So here is a question. Well, does f of x, which is just the exponential function, x to the n over n factorial, have an inverse in the formal power series? Yes. Okay. And if yes, what is the inverse? Okay, you're saying there is a constant term, but you haven't even started working on the homework. So how do you, well, okay, so what is the inverse? Can you? E to the negative x. All right, that is interesting. Okay, so indeed, proposition, which is inspired by calculus, is that the inverse of f of x is the exponential of negative x, and is g of x n greater than or equal to 0, negative x. Well, let me write it down like this. I want to write it down as an exponential generating function. Negative 1 to the n, x to the n, over n factorial, which is, yeah, so this is secretly, this is exp of negative x. And so as a disclaimer, in this case, because the series converge for all x, there is an argument which kind of claims that if two things converge everywhere, then and one is the inverse of the other, then this is true as formal power series. But I'd like to be careful. I want to see what happens. How do you prove it? How to prove this fact using just formal power series without knowing any calculus whatsoever. So how do you prove this? Well, you multiply, right? We have a formula for a product of two exponential generating functions. So let me try to apply that formula. F of x times g of x is equal to the sum of dn x to the n over n factorial. So I'd like to compute the right-hand side using the product formula here. So f of x is given by this form. So as an exponential generating function, your sequence is just the sequence of all ones. Right? If you look at the definition of the exponential generating function, the fn here are going to be all equal to 1. Is the exponential generating function of the sequence of all ans are equal to 1, and g of x is the exponential generating function of bn equal to -1 to the n. These are just the coefficients in front of x to the n over n factorial. So by the product formula, dn is, well, if I literally write down the sum, it's going to be the sum over I from 0 to n, and choose I times ai, which is 1, times b n minus I, which is -1 to the n minus I. Okay, so I can erase the 1. And what do I get? I get some alternating sum of binomial coefficients. What do I do now? Yeah, okay, binomial theorem, right. So that we have already computed this sum in class. So this is equal to either 1 if n is equal to 0 and to 0 otherwise. Because of the, let's say, binomial theorem, or you had a homework problem where you had to prove it bijectively. So just from previous lectures. And but the cool thing to me here is that, so this is a nice combinatorial effect. The number of sets of odd size is equal to the number of sets of even size. And you get it from just kind of, you get this fact by applying the intuition of the form exp of x times the exponential of -x is equal to 1. So this, I think, is kind of cool. You would think that these two facts are not quite related to each other, but they turn out to be almost. I don't want to say equivalent, but I want to say they are reflections of the same fact in two different languages. Yeah. So let me try to justify why I want to be careful. So why one has to be careful when translating from calculus to formal power series. So here's another example, which is very similar to the previous one, but it's slightly different. So exponential of x plus 1 is equal to e times the exponential of x. That's another obvious statement. So if I write it down as just both sides as formal power series, the sum over n greater than or equal to 0, x plus 1 to the n over n factorial is equal to e times the sum over n greater than or equal to 0, x to the n over n factorial. So what goes wrong with this formula? Oh. Yeah. So anybody want to take a wild guess? Maybe nothing goes wrong with this formula. Okay, the denominator. So n factorial. What's the which denominator? Or yeah. Okay, so nobody. Left-hand side does not converge. Okay, that's interesting. So if you look at the left-hand side, that's very close to correct, right? It's not that it doesn't converge, right? For all x's, there's the left-hand side and the right-hand side converge, and they give the same answer. It's not a power series. Nice. Yeah, that is exactly correct. Thank you. So this thing on the left is not a formal power series. To give me a formal power series, you have to tell me, you have to give me a coefficient of each of x to the I for all I, right? And to compute the coefficient, I have to expand infinitely many sums like this. Right? So in other words, each term contributes something to, let's say, the coefficient of x to the 0. each of these individual terms has a constant term. And yeah, it happens that these constant terms together form a convergent sum. But whatever, it doesn't matter. This is not a valid way to specify a formal power series. It has to be given without any calculus considerations. So you can't take an infinite sum of products like this if they all contribute to, let's say, the constant term. So yeah, but still. So yeah, that's what I mean. And in general, if you kind of just mindlessly manipulate some functions, you always have to keep in mind how to justify what happens at the hardware of formal power series. You have to make sure that all operations actually make sense. If you invert some power series, you have to make sure it's invertible. If you and if you specify something, you have to make sure that it's a formal power series. So, but other than that, I would like to mention that. So this sort of. Do I have time? I have time. So the kind of the main principle of how you can manipulate. Can you write E as a formal series, E000, and then the right-hand side is a product of formal series. Right, yeah, so the right-hand side is, this is a valid formal power series. Yeah, because yeah, any complex number or any polynomial with complex coefficients belongs to the ring of formal power series. The problem is the thing on the left. Right? Yeah. Why do we want a formal power series, you're saying? Well, working with formal power series allows us to not care about convergence. Right? So we can work with more general sequences, which do not necessarily converge. But the downside is that if we don't care whether things converge, then we have to, like, the objects have to be well defined. Right? If we're not allowed to substitute any kind of value of x into this sum, then we have to, like, what does this object even represent? It has to. Formal power series is basically a sequence of numbers. If you write down something like this, then this does not right away give me a sequence of complex numbers. Right? I have to perform some calculations. If I'm lucky, this is not guaranteed to give me a. I mean, maybe I should try. Here's another similar looking statement: x plus n factorial to the n over n factorial. If you try to think, like, this object does not make sense, right? Either as a formal power series or as a function of x. Like, it has no interpretation because its constant term is some infinite sum of natural numbers. You can't really talk about the coefficients of this series, nor you can talk about the values at any given x. Does it make sense? Or well, you mean the first statement or the second statement? Okay. The second one is correct as a statement about convergent power series from calculus. So in that context, it is mathematically correct. In the context of, if you're talking about formal power series, it is not a well-defined, it's not even a statement, because the left-hand side is not an object that we consider. Yeah. So if I were a computer and you were given me a program, then I would complain. I mean, if I was Java or something like this, then I would complain that this is not the object of the correct type. That's my complaint here. But the main principle that I want to state is that if something holds for functions from calculus, right, for convergent power series, and if all objects are well defined as formal power series, then the statement holds for formal power series. So that's completely not quite rigorous. There is a way to make this rigorous, which I'm not going to try to do, but you can basically use this with care. So if you can justify all operations at the level of formal power series, then it works. But yeah, you have to make sure you write down none of these things which do not make sense as formal power series, because then you can get actually something that's incorrect. You can get that the sum of all integers is like -1/12 or whatever. So you have to be very careful. And if you can just justify everything with the product formula, then that's the best kind of argument. And that's what I'm gonna try as hard as I can to just use the usual the formulas. I think everything is gonna work fine. But that's at least from the intuition standpoint, that is a very useful principle which I wanted to share with you. Yeah. So any questions so far? Yeah. Do we care about algebraic structure for formal power series? You mean like principle? Yeah, it has. Well, in this class we are not gonna discuss that, but in general, it's a nice ring. It is a principal ideal domain. It's like a local ring, whatever. It's a nice. It has nice properties, but yeah, we're just gonna be interested in applying this ring to counting balls in boxes and stuff like that. Any other questions? All right, if there's no questions, then thanks, and I will see you all on Friday, at which point I'll try to do some interest. So far, everything I've been doing is pretty useless, but on Friday I'll try to actually compute some stuff that's interesting. So see you on Friday. Sure. Okay. Well, if you write it in a different, I mean, like this thing on the right is a formal power series, and it's a representation of the same function of x. Right? Yeah. So yeah, it's a matter of how you write things down. It has to just this. Yeah. Go ahead. I mean, what I'm saying is that if all objects are defined as formal power series, then you get a statement about formal power series which is correct. If some of the objects are not well defined as formal power series, then you get a non-statement.